Hi there. In today's lecture, we are going to continue with the series Convergence Tests by looking at a few examples, going through the different tests that we looked at in the previous lecture. Okay, so let's start off with example number 1. We have the sum as n goes from 1 to infinity cos 1 over n squared. Okay, so this looks a bit difficult, but the first thing that you should always look for is the test for divergence. So what happens in the limit as n goes to infinity for each of these terms? So we see here cos of 1 over n squared. If n goes to infinity, then we get cos of 0, which is 1, and that means it fails that. Okay, because remember, we need to add smaller and smaller terms each time. If the limit of the terms ends up being 1, as in this case, the terms are not getting smaller, so we can't have convergence. Okay, so to do that, we need to show that the limit as n goes to infinity of one of these terms, so cos of 1 over n squared, this is going to be cos the limit as n goes to infinity, 1 over n squared. We know that this inside limit is going to be 0, so we have the cos of 0, which is 1, which is not 0. Okay, so we've used the test for divergence to show that this first one is divergent. Okay, so the terms are not getting smaller, which means it must diverge. Okay, so this series diverges. Diverges by the test for divergence. So you can abbreviate it TFD, or you can write it out fully. Okay, number 2. We have the sum as n goes from 1 to infinity, 2 to the minus 3n times 7 to the n. Okay, again, it looks a bit complicated, but notice how we just have number bases and we've got n in the exponent, which means this is very similar to a geometric series. We just need to put these terms together to see what the ratio should be. So here we can write this as the sum as n goes from 1 to infinity. The 2 to the minus 3n can go to the bottom, and the 7 will be at the top. So it will be 7 over 2 to the 3, all to the power n. But here we can simplify. This will be the sum as n goes from 1 to infinity, 7 over 8 to the n. And now this looks like the standard geometric series, with the ratio being 7 over 8. So the absolute value of the ratio, remember we need to take the absolute value, is equal to 7 over 8. This is indeed less than 1. So since the ratio is less than 1, we know that it converges. Okay, by the geometric series test. Okay, so you can abbreviate it like that. Okay, let's look at example number 3. Here we have the sum as n goes from 1 to infinity, minus 2 to the n factorial over n to the n. Now, just a little bit of advice or some hints when you're going through these problems. Whenever you have something with an n factorial, you should try to use the ratio test. Okay, so that's just a little bit of advice there. Whenever you have your n factorial in your series, you should use the ratio test. Now, that may not always work out, but it's a good starting point. Okay, so how do we use the ratio test? Well, we need to find the limit. We need to find the limit here as n goes to infinity of the absolute value of the next term divided by the current term. So n plus 1, that term divided by the nth term. So here we're going to have minus 2 to the n plus 1 factorial over n plus 1 to the n plus 1. So wherever we had an n, we put n plus 1 for the next term. Then we divide by the nth term, but that's the same thing as multiplying by the reciprocal, so we can multiply by n to the n over minus 2 to the n times n factorial. Okay, before we do any limits, we can clean this up a little bit. So the minus 2 to the n plus 1, we can write that as minus 2 to the n times minus 2. Just separating that. N plus 1 factorial, we can write that as n plus 1 times n factorial, just using the property of the factorials. N to the n, we can just leave that alone. Divided by n plus 1 to the n plus 1, we can write that as two terms. So it will be n plus 1 to the n times n plus 1 to the 1. And then we have minus 2 to the n, and we have n factorial. Okay, so this does look a bit more complicated than we started with, but notice that quite a few terms cancel out. So in the top we have minus 2 to the n, in the bottom we have minus 2 to the n, so they can go. In the top we have n plus 1, in the bottom we have n plus 1, so those can go. In the top we have n factorial, in the bottom we have n factorial, those can go. Okay, the minus 2, since it's inside an absolute value, we can take it out as a 2. So this will be 2, limit, n goes to infinity, and then we have absolute values. Technically, you can drop the absolute values because we're only working with natural numbers here, and it's not going to be negative, but you can leave it in. It doesn't hurt to leave it in. So here we have n to the n over n plus 1 to the n. Okay. Now, written like this, it's a little bit messy. We'd rather have that n plus 1 at the top. So we can swap the numerator and the denominator and just put the minus n as the exponent. So here we can have 2, limit as n goes to infinity. We can write this as n plus 1 to the minus n all over n to the minus n. Okay, so we'll see now why we swapped that. So we can write this as 2, limits n goes to infinity. We can write this as n plus 1 over n to the minus n. Now n plus 1 over n, that can simplify nicely. Okay, much better than what we had before. So this will be 2, limits as n goes to infinity, 1 plus 1 over n to the minus n. Okay, but I'm sure you've seen this limit before. This is the limit for the Euler constant, e. So we can write this as 2 times e to the minus 1 because we've got this minus over there. Okay, so this is going to be 2 over e. Okay, now you don't need to know the exact value of e, but here we do need to know that it is above 2. Okay, so it's 2 point something, which means we've got 2 divided by something bigger than 2, which means it's less than 1. Okay, remember for the ratio test, we're looking for if it is less than 1. If it is less than 1, then we know it converges. Okay, so here we didn't need to know exactly what e is, but you do need to know that e is slightly more than 2, and you'll see in your tutorial work, there's one question where you need to know that pi is slightly more than 3. Okay, so you will see that come up. Okay, let's look at some more examples. Number 4, we have the sum n goes from 1 to infinity, sine 2n over n plus 3 to the n. Now, another hint, whenever you have some trig function in the in this equation here, like sine or cosine, we know that sine and cosine alternate between positive and negative. So in fact here we've got an alternating series. So for some values of n it's going to be positive, for other values of n it will be negative. So in that case we should check for absolute convergence, because these trig functions, they alternate, but they're still bounded. So if we take the absolute value, it is also still bounded, and that allows us to remove these trig functions. So here, we can write this as the sum from n equals 1 to infinity, and now we take the absolute value since we're checking for absolute convergence. So sine to n over n plus 3 to the n absolute value. Now, like I said, the sine function is bounded between -1 and 1, which means the absolute value of the sine function is bounded below by 0 and bounded above by 1. So we have the following. Okay, so since it is never greater than 1, we can replace the function with 1, and that will make it smaller. Okay, since that function is less than 1. So this is less than or equal to the sum from n equals 1 to infinity. We've replaced the sine function with 1, so that makes this right-hand side bigger than what it was before. So that will be 1 over n plus 3 to the n. Okay. So here, previously, we had the sine function, which is less than 1, which makes that part smaller. On the right-hand side, we replaced it with 1, which makes the side bigger. So we've got this, the next line being bigger than the previous. Okay, we can introduce another inequality by noticing that in the denominator, we have this natural number, n. Okay, if we have a denominator with a natural number being added to it, that makes the denominator bigger. Okay, so adding a number in the bottom makes it bigger. If we take away that number, it makes this denominator smaller. And if you have a smaller denominator, you have a bigger fraction. If you've got a bigger denominator, you've got a smaller fraction. So if we take this away from the denominator, we end up with something bigger. So this is less than or equal to n equals 1 to infinity, 1 over 3 to the n. Okay, so just note these inequalities here, and knowing how to work with inequalities, that will be tested. Okay, so you should be comfortable with these manipulations. So here, we can write this as the sum from n equals 1 to infinity. We can write this as 1/3 to the n. Now, this is just a geometric series. We can take the absolute value of the ratio. We know that it's less than 1, which means it converges by the geometric series test. Okay, so what do we have here? We've got this series here converging. So this converges. In the previous line, we had something, that was there, over here. That means this one also converges. This one converges as well. Okay, why? Because it is smaller than something that converges. So remember when we looked at the direct comparison test, if we have two series where we take an arbitrary element from the one, if it's always smaller than the other one, if that other series converges, then the one that you're testing will also converge. Okay, so please look at the direct comparison test if that's confusing you. Okay, so that means this one converges, and again, we follow this up here. This previous one will also converge, okay, again, by the direct comparison test between the two. Now, if this one converges, then that means the previous one converges absolutely. Why? Because we took the absolute value of each individual term and showed that it still converges. So if something converges absolutely, then it indeed converges. Okay, so we've got this chain of arguments of why the original one converges. Okay, so please make sure when you are doing these problems that you put your reasons why each of them converge. So this last one converges for some reason, so the previous one converges, and then the previous one, all the way up to the original one that you were testing. Okay, you need to state the reasons for each of those. Okay, so that one was a little bit more complicated, and notice how we used more than one test. So sometimes for a given question, you will start off by using one test, and then in your calculation, you might need another test or another two tests. Okay, so it's not always one test per question. Okay, you might need more depending on the calculations that you need to do. Okay, so please just keep that in mind. Okay, let's look at number 5. So here we have the sum from n equals 2 to infinity of the natural log of n over n squared. And here we've got a hint. Okay, so sometimes I will provide a little bit of extra help to help with answering the question. So here we've got the natural log of n is always less than the square root of n. Okay, so we need to use this hint in our calculation. So since we've got the natural log of n is less than the square root of n as the hint, note how it relates to what we've got here. We've got the natural log of n over n squared. So to get from the hint to what we have here, we need to divide both sides by n squared. Now, n squared is always positive, so the inequality remains the same. But now, we've got our series here on the left-hand side, and we've got a new series here on the right-hand side. So what we can do is the direct comparison test. We can compare our series, the one on the left, to this one on the right. That's a bit simpler than the one that we started with. So this is less than the sum from n equals 2 to infinity of root n over n squared. Now, it doesn't look too simplified, but the root n we can write as n to the half. So we've got an exponent in the top, exponent in the bottom. We can use some exponent rules. We can write this as the sum from n equals 2 to infinity of 1 over n to the 3 over 2. Okay, so that's from the exponent a half at the top and 2 at the bottom. But now this is just one of our p series. Okay, in this case, p is equal to 3 over 2, which is indeed greater than 1, so it must converge by the p series test. So it converges by p series test. Now, if that one converges, note how the larger one converges, which means the smaller one must also converge by the direct comparison test. So since the larger one converged, that means our smaller one must also converge. So we have the sum, natural log of n over n squared, converges. How does it converge, or why does it converge? Converges by the direct comparison test. Okay, please make sure that you state your reasons every time you say that something converges or diverges. So here we said that this p was greater than 1, so it converges by the p series test. You need to state this full statement. So it converges and what test. So here it converges and what test. Okay, please make sure that you state both. Okay, let's have a look at another one, number 6. Here we have the sum from n equals 1 to infinity, 3n plus 1 over the square root of n to the 5 plus 4n squared plus 12. Okay, so now what we want to do is try and compare this to a series that we know either converges or diverges. So that's the easiest thing to do with these series. So we look at this and we see how can we relate this to something that we know. So notice that in the denominator, the highest order term is this n to the 5. Okay, so for very large values of n, this n to the 5 term will dominate. Okay, it will be much larger than the previous ones, these smaller ones here. So if this is much larger, in the limit, we can ignore those other ones. So what happens if we ignore those other ones there? And in the top, this 3n plus 1, again in the limit, the 3n will be much bigger than the 1, so we can ignore that. So let's see what happens. So we know that in the limit, okay, that meaning n going to infinity, we have the 3n plus 1 in the limit will be 3n, because the 3n is much bigger than the 1, and in the bottom, we're going to have root n to the 5, because that's going to be much bigger than those smaller terms. Okay, we can simplify this. This will be 3 over n to the 3 over 2. Okay, just by simplifying that a bit. So we've got this new series, 3 over n to the 3 over 2. And here, it's a p series, so p equals 3 over 2. That's bigger than 1, so it converges. Okay, so what have we done so far? We've looked at our series, we've looked at the terms here, and we saw that in the limit, this term, the 3n plus 1 over the square root n to the 5 plus 4n squared plus 12, this term looks like 3 over n to the 3 over 2 in the limit, which we know converges. So since we have something that converges in the limit, we should be using the limit comparison test. Okay, so these are the things that you should be looking for. So use the limit comparison test. Okay, so we took the limits of what we've got here. We ended up with a series that converges, so we should use the limit comparison test. Okay, so how does that work? That's going to be the limit as n goes to infinity, and then we have this fraction. In the top, we have the series that we're given, so the 3n plus 1 over all of that. So we're going to have 3n plus 1 over square root n to the 5 plus 4n squared plus 12. Okay, that's one at the top. And then at the bottom, that's the one that we're comparing it to, which is going to be this one here. Okay, that's the one that we're comparing to. So it's going to be divided by 3 over n to the 3 over 2. And then we take the limit and we see what we're going to get. So here we can do a little bit of cleanup. So we have the limit as n goes to infinity. This bottom fraction here, we can take the reciprocal and take it up to the top. So we end up with 3n to the 5 over 2 for the first bit, plus 3n to the 3 over 2, just multiplying this to the top, divided by 3 square root of n to the 5 plus 4n squared plus 12. Okay, now taking the limit is quite easy. I'll leave that for you to do. So in the end, we get the limit is 1, which is greater than 0. Okay, and since it's greater than 0, we know that this must converge. Okay, so this converges. Okay, we've got a few more to go through. So number 7. We have the sum as n goes from 3 to infinity, 1 over n natural log of n. Okay, so another hint, whenever you have functions like this, so 1 over n natural log of n, if we were to replace n with x, can we integrate the function? If you can, then you should try and use the integral test. So here, if we had the function f of x being 1 over x natural log of x, so if it's possible to integrate this, then we might be able to use the integral test. Now, remember that there's a few more conditions. So it needs to be continuous. It needs to be positive. And it needs to be decreasing. Okay, so just because you might be able to integrate that doesn't mean you can use the integral test. We need to satisfy these conditions as well. So yes, this is continuous, yes, it is positive, and yes, it is decreasing. I will leave that as a homework exercise to show it's decreasing. Okay, so look for your f prime and check that f prime is less than 0. Okay, that means it's decreasing. Okay, so remember to show that if this does come up in a test. So if you have to use the integral test, you need to show that it's continuous. It doesn't have to be a full proof, just say that it's continuous if it is. Positive, that's obvious in this case, and decreasing, you'll need to show that on the side. Okay, so show this. Okay, so that'll be a little exercise for you to do. Okay, but these three are true, so we can use the integral test. Okay, so what do? We replace the series with an integral. So we have the integral from 3 to infinity of 1 over x natural log of x dx. So we replace the n with x. Okay, for this it will be easy to do a u substitution. So u is the natural log of x, because du will give us 1 over x dx, which is what we need for that bit over there. Okay, so with this u substitution, we can write this as the integral from the natural log of 3. The natural log of infinity is infinity, so that stays infinity. And this will just be 1 over u du. So that takes care of the x as well as the natural log of x. Now the integral of 1 over u, that's going to be the natural log of u. So we have the natural log of u from the natural log of 3 to infinity. But if we substitute infinity, we get infinity, which means this diverges. So since the integral diverges, it means the series diverges. So the series diverges by the integral test. So remember, for the integral test, both the series and the integral will either both converge or they will both diverge. Okay, depending on what you get. Okay, a few more to go through. Let's look at number 8. So here we have the sum. N goes from 1 to infinity. We have 1 minus 1 over n to the n. Okay, so we did see this previously. If we look at this term just by itself, if we take the limit, then we know that this term goes to the Euler number e. Okay, so 1 over e, sorry, because we've got this minus sign here. So we know the limit is going to be 1 over e, which is not 0, right? The limit of these terms is non-zero, so it must diverge due to the test for divergence. Okay, so let's show that properly. So we want to show that the limit as n goes to infinity of 1 minus 1 over n to the n, we want to show that this is non-zero, which means it diverges. So let's call this limit L. Now, since we've got this n in the exponent, it's a bit annoying. We want to take it down. So let's take the natural log on both sides. So we get the limit as n goes to infinity n natural log of 1 minus 1 over n is equal to the natural log of L. Now we can take the limit using L'Hopital's rule. So this will be the limit as n goes to infinity, natural log of 1 minus 1 over n, over 1 over n, okay, standard L'Hopital rule stuff. So this is the natural log of L. Okay, now we can use L'Hopital's rule since this is in the correct indeterminate form. So we're going to have 1 over 1 minus 1 over n, and then chain rule, and we're going to get minus, 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 so plus 1 over n squared, all over minus 1 over n squared, and that's still the natural log of L. Okay, so some things cancel, and the minus we can take up to the top. So we get the limit as n goes to infinity, minus 1 over 1 minus 1 over n is equal to the natural log of L. Taking the limit is quite easy, we just get minus 1. So minus 1 equals natural log of L, which means L is equal to 1 over E. Okay, so this limit L is non-zero, which means the terms in the sequence are not getting smaller. So when we add them up in the series, we're adding terms that are not getting smaller each time. And if that's the case, then this must diverge. So this diverges. Okay, by the test for divergence. Okay, or you can abbreviate that as TFD. Okay, so you can use the abbreviations if you want. Okay, last one for today, number 9. We're going to have the sum, n goes from 1 to infinity, sine squared 1 over n. Okay, this one's a little bit tricky, so I'll go through it slowly. So what we want to do is rewrite this in a way that we can use the limit comparison test. Okay, so we use the limit comparison test. Limit comparison test with the sum as n goes from 1 to infinity of 1 over n squared, which we know converges. Okay, so we know it converges by the p-series test. Okay, so why do I choose this one? We'll see now. If we take the limit to do this limit comparison test, we end up with the limit as n goes to infinity, sine squared 1 over n divided by 1 over n squared. So those are the two series that we are interested in. The sine squared one, that's the one we're given. The 1 over n squared, that's the one we're comparing it to. Now, why did I choose the 1 over n squared? Well, because we've got the sine squared, we can write this as the limit as n goes to infinity. We can take one of the sine terms and one of the 1 over n terms and write it like this. Okay, so it went from being a squared term at the top and a squared term at the bottom to be two separate terms in brackets here. Okay, so this might still look a bit confusing, but let's do a change of variables. So I'm going to replace 1 over n with x. Okay, it doesn't have to be x, but that's just a dummy variable. So x goes to 0, sine of x over x, and we have sine of x over x. Now we know what the limit of this is. If we take the limits as x goes to 0 of sine of x over x, we know that that's going to be 1. So the first bracket is 1, the second bracket is 1, and so we just get 1, which is indeed greater than 0, so that means both converge. Okay, both converges. So remember, with the limit comparison test, we are comparing it to something that we know converges or diverges. Here we know this converges, so by the limit comparison test, the original one also converges. Okay, and you can see why I chose this 1 over n squared, because when we take the ratio, we get this term over here, sine 1 over n and 1 over n, which we know how to take the limit. So we know this limit. So that gives you an idea of how to choose your series. So you're given something, we need to choose another series, this one over here, such that when we take the ratio, we know the limit. Okay, so that gives you an idea of what you should choose. We also saw that in this previous example here. Let me find it here. When we chose a specific series, let me try to find it over here. So we had this series, we wanted to compare it to something else. So what we did was we chose this particular series, which we know converges. Why did we choose it? Well, because when we take the ratio, we can easily take the limit. Okay, so you shouldn't choose a series where it's difficult to take the limit. You should choose the simplest series that allows you to take the limit. Okay, and please remember those conditions. So if it's greater than 1, less than 1, or equal to 1, we know what happens in those cases. Okay, so here it is greater than 0, so both converge. Okay, that's going to be it for today. There are plenty more questions in the tutorial for you to try. Okay, so those are more of the test type questions that you'll get. So please go through that. I will be available on Wednesday, so just come to my office if you need any help with that, or you can send me an email. And then on Thursday, we will go through the tutorial as well. Okay, so that will be after the quiz on sequences. So we'll have a 10-minute quiz, very short, just on sequences, and then we will continue with the tutorial. Okay, please remember to have your tutorials written up so that you can submit them to the tutors. Okay, and please make sure that your name and student number is on all of the loose pages so that nothing goes missing. Okay, so I will see you in the tutorial. Okay, please email me if you have any issues at all.